Is it fine? Okay, good. So yes, thanks Federica for the introduction. So today, actually, if you want a caveat of the presentation, in the end, by looking again at the presentation and the slides, I will not give you too many answers and maybe not too many information. But what I try to do is to explain or re-explain some basic concepts which should be useful to understand what we mean by unfolding and what are the, I mean, this is supposed to trigger you to think about the various limitations of the unfolding and where the unfolding could help, where the unfolding cannot help, where the unfolding could be better than other things or other approaches in order to get our target, which could be generic or could be more specific to the workshop of this week. So let's first of all introduce what we mean by unfolding. This is supposed to be something, the upper part is supposed to be something more general. This is valid everywhere. So by unfolding, we mean going back from a distribution that is smeared by some effects to a distribution, I mean, to try to get rid of these smearing effects. Okay, and this is what we call unfolding. Of course, the opposite, by analogy, we call it folding. So by folding, in the rest of the presentation, I mean, we take the true distribution and then we pass it through the effect that is creating the smearing. Then if we go to collider physics, these smearing effects can come from different effects. Because sometimes we say, okay, unfolding means removing detector effects. But detector effects doesn't mean only detector resolution effect, so how well we measure the electrons, muons, or jets. It means specifically, I think we have an example, for instance, in the Atlas measurement, where these detector effects are also reconstruction effects. So also the fact that you have this imperfect TT bar reconstruction method that is not coming only from the detector resolution, but it's coming just, I don't know, from combinatorics or from other effects, I don't know, that can affect you. This is also entering the unfolding. Okay, so this is entering the smearing factor that requires you to do this unfolding. Okay, so then let me jump on something which is specific to this workshop. So this is just to give you an example why unfolding can matter even in this field. So this is just an unbiased random selection of two papers where I was involved at some point to try to understand the difference between the conclusions of these two papers that were claiming that, so in this first paper, it was claimed, okay, we can observe a Bell inequality violation with TT bar already with run2 data. And then this other paper was saying, no, we cannot even with the high luminosity. We are going closer, but no. And then we were trying to understand what is going on. Is the power of the observable very different and so on? And then in the end, my personal conclusion by looking at things was that what matters here is the way the unfolding is treated. So how much are we in the two papers is the unfolding treated? So what are the assumptions? What is done? What is not done? What is just guessed in a certain way or not? And so this means that the way we unfold, the way we go from the true, in this case, parton level distribution to the reconstruction level distribution or the detector level distribution with all the steps in between really matter here. So this means if you want to get a message is that if we are able to do all, I mean, the perfect reconstructions as in the previous talk, but also maybe a good unfolding technique, unfolding procedure, then we can go from this situation where we say, okay, we cannot do it, from a situation where we can do it. Okay, and this could be generalized to many other things. Okay, so then if you want an interlude, so do we always need unfolding? Actually, if you look at the various measurements from Atlas and CMS or the various collider experiments, actually, we don't always need unfolding. I personally discovered that, for instance, for B physics, for instance, in Bell 2, just to give an example of people concerning people who are here and we talked with this week, this is not usually done. Okay, the unfolding is not something that is usually done, while in Atlas and CMS these days we almost always do unfolding, but sometimes not. I mean, when we want to measure a total cross section, we usually don't do unfolding because we don't need it. And actually, even when we want to measure some shape or something that you might think that you need unfolding, you have other methods. So you can say, okay, I want to extract some measurement which depends on the shape. So I don't unfold the distribution and then extract from the unfolded distribution the information, but I do what we call template fit at the detector level. Okay, and this is an unbiased example. This is an Atlas top mass measurement, where even if the observable is not exactly the full top mass reconstructed, is just a partial mass where we could think about going through the unfolding. Here, this is not done, and actually you have a fit that is done at the detector level by, if you want, folding various hypotheses of the top mass with some transportation, some detector resolution and so on, in order to get the templates at the reconstruction level. Okay, and this is another example which we talked already about. So for this Atlas entanglement observation and in TT bar events, here, as Jay already commented, here in the end, what is done is not an unfolding, but is using this calibration curve where we have these points that are obtained and by trying to change, let's say, quotation marks, the amount of entanglement, and this is probably a delicate thing to think about. But then, assuming that you can do it, then you can calibrate your measurement and then get your let's say, reconstruction level value or values, and then turn them into what you're interested in. Okay, so we don't always need unfolding, but actually here I try to put some maybe naive situation. You can guess who is the experimentalist and who is the theorist here. And so this is probably exaggerating a little bit, but okay, if you don't do unfolding, then the experimentalist goes to the theorist and tells, okay, this is my result, full stop, okay? This is a number or something. Then the theorist might be okay, but then maybe many things can happen. So here in this example, okay, the number is probably depending on some modeling or some model, right? And then the theorist has a new model, and then what do? You need to pass through the detector simulation again, this new model, to get a new number. But then maybe this is not feasible. This takes too much time. And instead, ideally, if you give enough information to the theorist to do everything by himself or herself, then this is much better, even for us experimentalists. We can go on vacation finally, okay? And so this is just for fun, but it has some probably level of truth. Then you might have other benefits. So even if you want to, this is not always true, but sometimes it could be true. This could be useful for combination of more information. So if you want to combine channel signal regions and beams, this could be easier with when you have an unfolded distribution. Could be even harder. Depends on the case and the technicalities. And then this is a little bit a delicate point. So in principle, by using unfolding, you can improve the precision of something. But of course, if you want to improve something, it means that you have to insert some inputs from outside. So you have to insert some bias. And you can think, okay, I don't want any bias, but this bias could be well motivated. So with the unfolding, you have the technical possibility of inserting some external knowledge, some assumptions, in order to make your measurement more precise. Of course, sometimes is something good to do. Sometimes it's definitely something not good to do. But we will see a little bit more about this in the following. I don't know why it's not. Okay, now it's working again. Okay, so let's go to a little bit more practical part. So what about, let's talk about what we call binned unfolding. So I will have a final slide where I mention also the possibility to do the unfolding in particle physics without bins, but let's consider just the bin distribution. So we start with a bin truth level distribution, and we have a binned reconstruction level distribution. Of course, we start with this and we go this. If we consider the folding procedure, which we do, for instance, with a simulation. But then what we want to do for the unfolding is to go from the reconstruction level distribution or from the detector level to the truth level. Okay, so this is a simple case where you have the same number of bins here and here. So then we can formalize in a very simple way, just with a matrix here. Okay, this is the truth. These are the truth bins. These are the detector bins, and this is just what we call the response matrix. Sometimes, by the way, you hear a migration matrix. What does it mean, migration matrix? Migration matrix is just, if you want let's say a transformation of the response matrix, where we try to get out, pull out the acceptance and efficiency effects, and you have just the effect of migration, as the word tells, between bins. So just to visualize it better, if you want. But the full matrix, we call it response matrix. Okay, so again, experimentalists say, okay, this is simple. We are maybe sometimes too naive, but this is what sometimes you could do. Okay, I just invert the matrix, right? This is not difficult. And so, of course, you can do it only if you have the same number of bins, but actually you can say, okay, I'm a little bit more clever, and as an experimentalist, I also like to complicate my life a little bit more. And then I say, okay, inverting the matrix is numerically equivalent to use a maximum likelihood principle, which we all like a lot. And then we move from this matrix inversion to a maximum likelihood unfolding, which has a numerical benefit sometimes, because sometimes if you have complicated things, it's easier to minimize a chi-square if you want, so a negative log likelihood, than to invert a matrix. This is one thing. And then the other advantage is that this matrix could be rectangular and not square. So you can have more reconstruction level bins than truth bins. So this is a small advantage. But in general, the two things in particular conditions are basically the same. Okay, is this, okay, so it's a small interlude. So in this approach, what do we do with the first complication? So what we do with the background and with the systematic uncertainties. Actually, this treatment is in principle simple. So with the background events, we just subtract them. So here, instead of just the data counts, we subtract the predicted number of background events. And then we have to ask ourselves where the systematic uncertainties go, because we always have systematic uncertainties. And this, I think, this is important, because sometimes naively, when you have a student, he or her doesn't understand immediately where the systematic uncertainties go when we have unfolding. And actually, you have to remember that systematic uncertainties go in this formalism only where in the response matrix. So actually, in the matrix itself, not in the inversion of the matrix, and of course in the background subtraction. Okay, this is important, because then a systematic uncertainty is zero if it's not affecting your background and is not affecting your response matrix. Okay, good. Then, is this always working? Actually, no. People might know. We all, as experimentalists, we should all know that if you do it too naively, this matrix inversion or maximum likelihood unfolding, you get these fluctuations, these oscillations, these jumps. Where are they coming from? Actually, they are not coming from numerical precision in the inversion or anything like this. So even if you are able to numerically invert the matrix with infinite precision, you still get this effect. So this doesn't have to do with the numerical precision. This has to do with the fact that you have off-diagonal elements in your migration matrix or in your response matrix. And so if you have this, then you have these jumps here. If you want to understand them better, I mean, I like to try to understand this by considering the the likelihood, the maximum likelihood unfolding, where you treat each of the truth level bins that you extract as a parameter, okay, a parameter of the fit, and then you can draw the correlation between these parameters. And actually here, this color code tells you whether you have a correlation or an anti-correlation between neighbor bins. And actually here you see that these red ones are just the identity, the same parameter, but then you see that the neighbor bins, they have negative correlation. And then again, they have a positive correlation. So you have this oscillation of the correlation between the bins. And this is basically, if you want, the underlying effect that is creating these oscillations here. We will come back to this in a while, but usually we want to try to avoid or mitigate this effect for various reasons that maybe we'll discuss at the end. The first thing is just if you're thinking about, I don't know, showing something in a paper, you don't want to show something like this. Okay, this is the naive thing, but also you might have other reasons why you don't want to show something like this as a result. Okay, so you have here a list of solutions. Some of them will not really work. So beam by beam correction is just to say, okay, I just you know what to do. I just ignore these beams and make a further approximation. So I ignore the off-diagonal beams and I do the unfolding without it, and I will not have this effect. But this is, of course, putting some bias, inserting some bias. So your result will not be strictly speaking correct. Then you could do something instead very sensible, and actually we sometimes forget about this. So if you tune a little bit, the binning and you improve the resolution, you can reduce this effect. Or you can, if you have more detector level beams than truth beams in the likelihood unfolding, for instance, you could again mitigate a little bit this effect. But what we usually try to do is what we call regularization here. So I will explain you in a couple of minutes what regularization is without going into the details. So let me use the likelihood method, which for me is easier to explain what we mean by regularization and how regularization means. So regularization means putting some external constraints in order to dump the oscillations. And so in the likelihood approach, we just do it by adding a piece or multiplying the likelihood by a piece, which means adding something to the corresponding chi-square, which are basically some constraint terms on the parameters that we are extracting. So we insert some bias, and in this simple case, the bias is just some previous, let's say, the starting values of the beams, so of the parameters, and this tau is controlling the strength of the regularization. Then you can have more sensible shapes of these constraints, like I don't want to just bias the value, but I want just to make sure that they are not oscillating, so I constrain the derivatives. So for instance, the second derivative of my shape, and this is what is usually done. It works quite well. And so actually this is an example of trying to apply this kind of regularization with a certain choice of the strength of the regularization, and you see that things seem to work quite nicely. You reduce the fluctuations, you reduce the anti-correlation, so okay, this seems to work. Of course, the problem is that when you do it, you are inevitably adding a bias. So whenever you have a regularization, you always have a bias. Then this bias could be irrelevant, could be negligible, or could be something you want, but you always have a bias. It's impossible to avoid it. And so usually we do this stress test in order to quantify how much is this bias. And in general, to do this stress test, we basically produce some pseudo data, for instance, with some alternative truth distributions. We fold them, so we create some pseudo detector level data. Then we unfold this data by using the same, let's say, the regularization, which is based on our nominal model. So it's not, we don't change the migration metrics or the response metric. We don't change the regularization. And then we get something that, in general, if we have a regularization, will not match exactly the starting distribution. So you go to the detector level, you go back to truth, and you find something different than your starting one. This is just because of the bias. And then in this way, you can quantify your bias. Then there are various ways of doing. You insert some linear slope, or you use alternative models, and so on. Okay, so this is just to flash you this. If you hear iterative Bayesian unfolding, this is just a technical way of doing this regularized unfolding, which is not based on likelihood and is very often used. I will not spend too much time on it. It's just that you have to know that this is always regularized, and you can control the strength of the regularization by changing the number of iterations. You have another thing. So I will tell you about what I call profile likelihood unfolding, and this is based on the concept of the profile likelihood. I hope that most of you are familiar with it, but if not, here in these couple of slides, I have some information. So the idea is that you put your systematic uncertainties inside your statistical model. Okay, and that's basically it. How do you do it? You assign to each source of systematic uncertainty, each independent source of systematic uncertainty, an unknown parameter. But this parameter is not completely unknown, but it has a constraint term in the likelihood. And so by doing it, you do the fit once, and you have the full result with all the systematic uncertainties. This is the main concept. So this, in my mind, is the most important advantage of profile likelihood fit. These are some details. The most important thing is whenever you do a fit with a profile likelihood, you get a value not only of the parameter you are measuring, but also a set of values for all the parameters associated with systematic uncertainties, which we call systematic uncertainties. Okay, this was a very quick description of what is a profile likelihood fit. We can use this inside the unfolding because we have the likelihood unfolding, and we can turn it into profile likelihood unfolding. And this is something that is used, is not done super often, but is being done. I'm almost done. More and more recently. And so the idea here is that we, instead of just extracting one parameter, we extract several parameters, which are our truth beans that we want to think. So we do the same step as moving from likelihood fit to profile to likelihood unfolding, and we just add the profiling here, if you want, the systematic uncertainties and these parameters. Flashing you just some results for par condicio, let's say, one from CMS and one recent from Atlas, where this is actually done. So this profile likelihood unfolding, where you have several benefits that you can combine more information, you can have the result with all the correlations and everything inside. Here in this result from Atlas, we even have the regularization added to the profile likelihood unfolding. So this is a regularized profile likelihood unfolding. So this is even putting everything together. Sorry if I'm taking 1 or 2 minutes more. Hope this is not a problem. So, but I want to go to the point. So this is an ideal case of what we could do with the unfolding in our case of entanglement or Bell inequalities, specifically in TT bar. This is just to show you some really let's say, complicated scenario where you want to have the full map of, in this case, in the TT bar case, MTT bar, scattering angle. And then for each of these beans, you want to have the full 9, so 3 by 3 matrix. And each element of this matrix, if you want to use fully the unfolding, should be a distribution, okay? A distribution of the product of the cosines of the angles in this binary system, no? And so if you think about it, this is a lot of beans. A lot of beans, a lot of distributions, and something could actually go wrong technically, numerically. And actually, this is an example. This is courtesy some plots done by Jay. Actually, I wrote it somewhere. Yes, here it is there. And this is just a quick explanation of why the unfolding was not working for the Atlas result of the entanglement. So this was the result of the stress test that I was mentioning you before. For the inclusive case, so when you try to unfold the cos phi inclusively without cutting on MTT bar, and this is instead when you cut on MTT bar. So you see that here the various colors, so these are not closing perfectly, and also you have more fluctuations and everything. So things start to go a little bit wrong, both in terms of fluctuations and in terms of bias. And so you could imagine when you try to do it for all those beans there, so you might have technical problems. Okay, I will skip this. I hope it's clear where this could be useful, profile likelihood unfolding. Maybe for cases where you have a lot of background, this could be particularly important, so even non-TT bar, other things. And yes, these are more for discussion, whether we need to regularize or not, and whether unfolding is model independent or not. And let me finish instead saying that we have other methods that I didn't mention, and we have new methods. Maybe this is an example of unbinned unfolding that we should maybe try to investigate. And this is maybe another method which is not unbinned, this is still binned, but maybe is quite related to the workshop today. So it's just this is trying to use quantum technologies somehow to have a more efficient unfolding. Okay, thanks.
Questions?
Thanks. This was very clear. Sorry if I missed it, but you discussed profile likelihood unfolding, right? So this is one method that we use, and there is also the other one, iterative bayesian unfolding.
Yes.
Can you maybe mention a bit about the main differences between both?
Actually, in principle, there are not too many differences. So the two are equivalent in certain circumstances. Okay. So in the iterative Bayesian unfolding, sorry, you mean the iterative Bayesian unfolding, not the full Bayesian unfolding. Yeah,
the iterative, yes.
Yeah, because it exists a full Bayesian unfolding, which is actually equivalent to the profile likelihood unfolding, which is still based on likelihood. Instead, what we call here iterative Bayesian unfolding, the difference is that here you don't try to, if you want to use the maximum likelihood principle here, but you want to just update your information based on the data and some prior, and you do it iteratively. So this is the main idea. So you have some prior, which is depending on your nominal distribution for the truth distribution. And then you sort of do a combination between the data and your prior knowledge. And so you update your prior knowledge. You do it once, you do it twice, and so on. And at some point, this gives you sensible unfolding. So this is the idea, because in this way, you have the regularization intrinsically added to the model by this prior without having to, I don't know, construct some terms.
Are there different problems that can come from using this and not profile likelihood unfolding?
So to some extent, they can give you more or less the same results if you have regularization in the profile likelihood unfolding. The one difference is that here you have regularization by construction. So in order to not have regularization, you should go to infinite number of iterations. The other and instead here you should add it by hand, the regularization. The other, if you want to difference, is that with profile likelihood unfolding, you can do, in my mind, you can do more, because you can add more, you can add control regions, you can combine this with some other measurements, you can estimate the background at the same time, you have the possibility to constrain the systematics if you add more information, and so constrain the Nice's parameters and so on. Of course, this sometimes is dangerous. So if you want to have something that kind of works by construction, you usually use this, because this, you know, that is safer. You don't risk to do something too wrong by doing this.
I just wanted to highlight that point exactly, that it is they're suited for different problems, and you don't need a one-size-fits-all thing, as Michele said at the beginning. But one of the places where you get the power in the profile likelihood fit is in the systematic uncertainties, because you constrain them with they enter directly as nuisance parameters where you have to put them into iterative Bayesian. The danger there is that the Gaussian assumption of those uncertainties enters extremely strongly, which is fine for some of them, but for things like 2-point Monte Carlo uncertainties, you're really making a very strong assumption that there's a Gaussian shape to that to be able to constrain it in the first place. So this can be, yeah. So
yes,
they're suited for different problems.
This is a good point. So in the profile likelihood fit, and then also in the unfolding, we have to assume that we have a continuous dependency on the parameters that are controlling the systematic uncertainty. And actually, in order to make it working numerically, we had to also make them Gaussian or regular distributed.
I had one comment to your unfolding part, right? That usually one thing that we talk is correlations, right? Talk a lot about correlations, but with unfolding in particular, right? Sometimes that gets lost. So if you measure whatever the whole spin density matrix, right, then, which is something similar to equality, right? You better figure out all the correlations between systematics and all your bins and so on, right? That has an impact on your final precision for your measurement, right? And if you only look at one distribution, then of course we project out the rest.
Yes. Correlations are very important. So correlation between everything. So between the results and correlation between the systematic uncertainties. And actually with the profile likelihood unfolding, in principle, you could get them correct, or at least you could get them fully. If you have the coherent treatment in these two things, then you can even combine afterward everything. If you have everything done with the profile likelihood unfolding, sometimes it's technically difficult. I think it's important the numerical precision here. Because we discussed recently that when you have large anti-correlations and correlations in the unfolding, then the numerical precision is hitting you. And so the result, especially in terms of correlation, could be incorrect numerically.
I think a good exercise is if the experiments do internally try to invert their own covariance matrix, which at times wasn't done in the past, right? And then it goes.
An obvious closure test. That's
Yes.
exactly not that.
Eric.
Thank you, Michele, for this nice review, very clear and helpful. So let me comment on the unfolding method that we used, since you quoted the result at the very beginning of what we did. Unfortunately, Claudio is not here because he's the guy that did the job, but I can comment for him. So what we did actually is okay, we used the Bayesian unfolding, but we found we also tried all the other methods. So SVD with all the possible regularization methods, going from large value. We moved through the SVD, then we moved through other maxent, maximum entropy, and so on. So we moved, and the result was very robust with respect to the unfolding method. He tried to also to make a stress and closure test by using a synthetic correlation matrix, in which he checked not only the expectation value that was correct, but also the significance by trying to simulate both a standard model and non-standard model correlation matrix. So I don't think that the problem arises from the unfolding method that we use.
Well, the thing is simpler. So for the first paper, there was no unfolding. Okay, so this is my message was, by considering also the let's say the degradation of the sensitivity that is coming from the folding or the unfolding, you can really completely change the answer. And so the way you do the unfolding could this probably, I mean, as you said, this was the maximum, the most precise thing that could be done, without adding, of course, without adding more information.
No, but the problem, Michele, is that there is not only the unfolding as a difference between it, there is a completely different method that is used to provide the Bell inequalities violation.
But, yes, so really the observable, the definition of the observable in the end is not making a huge difference. So really, I tried myself at at Parton level, and in the end, using as much as possible the same settings, and the two were equivalent at Parton level. Then when moving to the detector level, then you had differences, because here the detector level was done, let's say, in a simpler way, without having to do all the
what I mean is that the basic difference is the choice of the optimal basis. That's the basic difference.
Yeah, but this is not doing any, this is what I'm telling. I tested it, and this was not giving a huge difference.
Well, of course, it has to produce a bias. If you optimize your basis on the basis of the data, of course there is a bias. You know?
This is going a little bit outside.
Yes, outside, but no, just to tell you that it is not unfolding the difference between these two papers.
But actually it is, because here the bias was corrected. Yeah. The bias was corrected for. So in the end, the observables were performing very
we will discuss offline, but and I think that the very this is something that we should clarify here once for all. When fix it before seeing your data. Otherwise, you produce a bias. This is something that, if you want to converge on this point, is important to say clear. You always find something which is completely biased towards.
Yes.
Okay.
Sorry, I have a very basic question. From the theoretical point of view, how can I? Typically, you guys, you do have a regularized unfolding, and so you start with the unregularized unfolding, and then you move on and implement a regularized unfolding, or you just start from the very beginning a regularized unfolding?
It depends. It depends.
So how what's the
sometimes you just directly go with this, because I said this is a kind of, this is quite easy to use, I would say, unfolding, that gives you most of the time something reasonable, something sensible, and then you just play around with the regularization strength and you make sure that your result is not changing too much by changing the regularization strength. So in this case, the number of iterations. So in this case, you start already with a regularized unfolding.
So
Sometimes you start with the unregularized, you see that you have some crazy fluctuations, some unphysical results, and then you said, I want to edit. But it's not always like that. Depends on which method you use.
then you have this tau parameter, right?
Yes.
You are going to vary it. So when are you happy with it? What's the
What do you
what's the test that you want to check that you think that
Yeah, so to determine the optimal, let's say, regularization strength value or the regularization level, you have to do some optimization, and this optimization has as figures of merit both actually how large are your fluctuations, or actually your expected fluctuations, so the variance of the result. And in parallel, you also do the stress test that I was mentioning. So to make sure that the bias is not increasing too much. Many times this is not done automatically. So the variance check is done more or less automatically. And then once you find some optimal value here, then you check that the bias is not too large. But you always have these two things. So you try to dump the fluctuations, quantifying them a little bit in some way, and then you make sure that the bias is not relevant.
Lately, we are using the minimization of the average correlation factor, right?
What?
In more recent papers, we are using the minimization of the average correlation factor, right?
Yes.
To deal.
Also,
A comment on the second
So-
bit for the tau regularization. I mean, you can look at the polls and check that you haven't overly constrained your uncertainties, right? You see if you have strongly regularized you get polls with widths much lower than 1, but it's very much done sort of by eye. But for the first part of your question, I think the entanglement result is a really good example of how you decide which one to do, because the history of that is we started off by default trying to do a profile likelihood fit, and then we realized we couldn't get that to work, so we tried an iterative Bayesian unfolding, which is somewhat weaker in its assumptions, and we couldn't even get that to work, so we ended up to the calibration curve. So you start off with one choice, and then you see if it's like going horribly wrong, you have to change it. But I don't think you should say we often sit down at the beginning and think, right, okay, which one should we do? You try the hardest one first and the best one first, and then you sort of go down as you fail.
Yeah. You can sort of see coming when you need regularization, right? If you're pushing the bins to below your resolution, you're going to get in trouble, and you're going to need some way to fix that. Is that fair?
What do you mean that we have no data there? No, this was just a toy example by Stefan Schmidt from
but you have
another-
some data points and some like something that's very, very few GV.
very small GV, but I think this was really completely toy. This was
Okay.
not passed through any reasonable thing. Yes, it was. Okay, thanks.
Sorry, I just want to, if you can show the slide with the cartoons, I have a very obvious statement, but I prefer to remind the one before with the hat, and yeah.
Yes.
So I mean, what you say, of course, is true, but there is also the other pitfall that you exaggerate with unfolding, right? I mean, in the sense that if you go back to particle level, then you are also inserting the theory one, and in the past we had problems with that too, in fact. Right? I mean, if you go to particle level, I mean, you are unfolding on the Monte Carlo, which means then that you are putting in a Monte Carlo information back to the particle level.
Yes.
So then if I want to use as a theorist, unless I know and I do the, I go forward and backward, I see what was the effect of the Monte Carlo, then I will lose that information and then we'll get a degradation of my information. So there is like an optimal point which you can do the unfolding, which is clear, which is the detector, right? Then if you go further,
Okay.
then you're unfolding on stuff that this is a theoretical that might change in time. So we had historically we had a huge issue with for example, the B fragmentation function, right, in the past and so on. So It's
Yeah,
also important
this
to
is
say,
true. This is probably what you're saying, that this is true if this unfolding is done just removing the experimental effects and not the Monte Carlo
Right,
effects from
right. So,
hadronization and this sort of thing.
yeah, there
Yes,
is an optimal place where to do it. Thank you.
I agree.
Okay, thanks again, Michele. Okay, now we have the last talk of the first part of the morning.